So this is your last lecture in the Unit 2 Electrochemistry unit, and we're going to pull together what you know about stoichiometry with what you know about electrochemistry. So this unit encompasses basically everything from using your reduction potential chart to determining voltaic cells to determining electrolysis, and finally to figuring out, if you're using electrolysis, the mass or the amount of substance that can be plated using a certain current, that can be attached to a cathode using a certain current. So that word plating we'll talk about in a minute. So the first thing that you're going to do is the same thing you've been doing, and that would be make sure that you complete these learning targets. It's a short list this time, and you can find most of it right there on page 980 in your book. So start there. And then when you are pause the video, and when you're finished, then you can start the video again. So go ahead and pause. Okay, so now that you have an introduction, you can restart the video, and let's see what's happening here. We are still using our reduction potential chart, but not as much in this situation as we have been, because we don't remember that the potentials are not stoichiometric relationships, that the reduction potential is just a comparison to hydrogen. That's the likelihood of the reduction occurring compared to how likely hydrogen would be to reduce. So this is very similar to what you did in your lab, comparing your items to zinc. And so because of that, there's no stoichiometric situation. And remember that you're not multiplying the reduction potentials by the numbers of electrons when you have to even out electrons, etc. So the coefficients are irrelevant to the potential. But when we do stoichiometry, the coefficients are not irrelevant. So this part of the unit, this part of your calculations, you'll have to make sure that you're careful to know the coefficients in your half reactions, or the number of moles of electrons in your half reactions, or the coefficients in your overall equation. So let's go ahead and look at it and see what's going on. So as you did your targets, you should have discovered that Michael Faraday is the scientist who is credited with the law that describes the quantitative relationship between current, which is a flowing charge, a moving charge, in this case moving electrons, and the amount of product that can be created by an electrochemical reaction due to those electrons. So Michael Faraday, we give him the credit, and he's the one who discovered that, mathematically speaking, 96,500 approximately, 96,485, I think, coulombs equals 1 mole of electrons. And so you have to kind of know what a coulomb is. That would be the charge, right? And so we're looking at that idea of this is a new conversion factor. So Faraday's constant is something that you should remember. So make sure that you have it in your notes. And then, sorry, I need to connect my Apple Pencil, but make sure that you have it in your notes, and then make sure that you are ready to use it as we keep going here. So this is definitely a memorization piece. This is a big star. All right. This is one new conversion factor. You can use the moles of electrons then in your half reactions to go from the coulombs through moles of electrons to moles of substance, moles of metal, or moles of whoever's being reduced, so or who's being produced in the reduction. So this is kind of where we're headed. The other thing that you want to look at is that we can talk about electrical current, and this should also already be in your notes, in your learning targets. But we measure electrical current in something called amps, and you've heard of that probably with the electrical circuits in your house. But 1 ampere is equal to 1 coulomb per second. All right, so this is a movement of electrical current. And amperes are a description, or amps are a description of the charge that's moving through a certain place, through a certain point, over a certain period of time. And in this case, we talk about seconds. So the SI unit is basically our conversion factor, that 1 amp is 1 coulomb per second. So notice that if I have a current that's not 1 amp, that would be a current, the current is, let's say, 5 amps. Now that means it's 5 coulombs per second. So if you had a current of 17.3 amps, then this would be the same conversion factor as 17.3 coulombs equals 1 second. So you want to really start to think that these are both conversion factors. All right, so you need to memorize the ideas of this and how you use it. And you would be either solving for current, which means you're solving for how many coulombs per second, or you're going to use the current as a conversion factor to go between time and the current to get you to coulombs to get you to moles of electrons. So I'll give you a short version of how this works. The first thing you need is the balanced redox equation with the number of electrons transferred. So it's easiest actually to do this in half reactions. So let's say I have the reduction of aluminum ions. This would be Al3 plus 3 electrons yields Al, basically telling us that for every 3 moles of electrons in this case, we can convert 1 mole of Al3 plus into 1 mole of Al, and that's coming from the coefficients on those substances. So notice the coefficient of 3 electrons here is the same as saying 3 moles of electrons, just like the coefficient of 1 that you can't see in front of the aluminums is like saying 1 mole of aluminum and aluminum ions, okay? So this is using stoichiometry the way you have been doing it. There's basically 2 options. You're going to start with time, and you can find the amount of metal plated. So this would be the amount of metal produced, and it's going to stick to the cathode because this reaction is occurring in solution, and the aluminum ions would then be stuck to the cathode as solid aluminum. So if I wanted to plate something in aluminum, I don't know why I would, but if I wanted to, I could use this solution and I could run electrical current through it, and the aluminum would stick to the cathode. And I would have to make sure that I am using something that's a very good conductor of electricity, obviously, as my cathode, but the aluminum would stick to the cathode and it would be covered in aluminum. We call that plated. So often, like silver, ornamental silver, like silverware, or like silver trays, or display dishes, or things like that, are often silver plated instead of solid silver. And you know now that from your lab, the solid silver is actually fairly malleable, so it's not very good to use solid silver for things. You wouldn't want to make a knife out of solid silver, but we could definitely plate something else with silver so that it's more valuable, more beautiful, etc. So this electroplating is often what we do, and we'll see another example of copper plating in a few minutes. So I just want you to kind of understand the terminology. So either you're going to start with time and figure out the amount that's plated, and the thing that works is really well to go through there. We'll talk about that. Or you could be solving for the moles of electrons. And if you use the moles of electrons and I gave you choices, then you might be able to tell me maybe in this reaction it produces 3 moles of electrons, or it uses 3 moles of electrons. In the case of this aluminum reaction, I could decide that the ion that was being reduced had to be a 3+ ion. And you'll see about this. We'll do an example of this in class as you're reviewing and things like that. So this is an important trick, but this is something that College Board likes to use. Technically, you could also start with time and solve for moles, so that if you were given the grams, like you could end your stoichiometry with moles down here. And if you were given the number of grams, then you could solve for molar mass, because molar mass is the number of grams of a sample that's equal to the number of moles of a sample, right? So if you were given grams in your question and you said maybe it plated out 15 grams of an unknown metal, and you could do your stoichiometry using the time and the current, then you could find moles, and you would substitute in the grams that you were given and the moles that you solved for to find the molar mass, which would then let you identify the metal given a limited list, right? So this is another trick that's a really good College Board trick, and we'll work with some of that together in class as well. So that's one option. Start with time and go to amount, usually, in moles or grams. okay? Or you can go backwards from that. You can start with the amount, or you could even start with the moles of electrons and find how much time it took to plate that much, or the current that might be required. And so if you're solving for time, that's relatively straightforward. But if you're solving for current, you have to remember that amperes are coulombs per second. So what you would do in this case is you would solve for coulombs from your stoichiometry, and you would have to be given the time in the question. They'd have to say 10 seconds or 5 minutes or whatever, and you would divide your coulombs that you solved for by the time in seconds. You have to be careful, they like to give it to you in minutes or hours, and so you get that, and then you can solve for the current, which would be the amps. So these are your options. All right, so that's kind of a long process of talking through it, but let's go ahead and do a couple of examples, and you'll be able to see a little bit better how this works. Okay, so in this example, you may want to pause the video so that you can write the question of the example into your notes, and then we'll solve it together. So go ahead and pause the video if you need to, and then restart it. So in this question, they're telling us a current of 5.3 amps. And the very first thing my brain says is if I know this current is 5.3 amps, then I know that in this case only, 5.3 coulombs equals 1 second, because 5.3 amps is the same as 5.3 coulombs per second. All right, so this is a really important way to interpret the question. And they give us an amount of time. They said that we're going to apply this current for 10.8 minutes to a solution of aluminum sulfate, and I want to know how many grams of aluminum will be obtained. So this is solid aluminum, and aluminum sulfate has the aluminum ion in it. And so we need to think about the half reaction that's going on here. So if we're going to take the aluminum ion and we're going to reduce it to solid aluminum, that means that my equation has to have 3 moles of electrons. So this is the same one that I gave you an example before. All right. So now this is the example where we're going to start with time up here. And they're asking for how many grams of solid aluminum can I obtain? So we're going to start with our time. And I do it all in dimensional analysis. So 10.8 minutes. And in order to use my new conversion factor of amperes or coulombs equals 1 second, I have to make sure that my time is in seconds. So I'm going to convert time from minutes to seconds first. 1 minute and 60 seconds. And that allows me to use my new conversion factor. So I need to get rid of seconds, and I'm going to go to coulombs. So this would be, in this case only, because they gave me the current, 5.3 coulombs per second. Remember, this is from the amps that were given. Okay. And then in order to get from current to, or charge to moles of anything, to be able to use my equation, I have to get to moles of electrons. And so I need to get rid of coulombs and get moles of electrons. And the definition of that is from Faraday. So this is from Faraday's constant. Okay. And remember that that's here. If you didn't write it down, that's this 96,500 coulombs equals 1 mole of electrons. So we'll do 1 mole of electrons, 96,500. If you're given more than 3 sig figs, technically you should make it 96,485. But if you're given only 3 sig figs, and usually that's what College Board does, then it's okay to simply use 96,500. So this gets me to moles of electrons, and you can cancel things out if you need to see that. And I don't care about moles of electrons. They wanted to know about solid aluminum. So here's where I need my half reaction. I'm going to talk about moles of electrons, 2 moles of aluminum, and then they wanted grams, so I have to go one more step. Moles of aluminum to grams of aluminum. I'm about out of room. And so these two, this one comes from the half reaction, and the last one you're good at. This one comes from the periodic table, right? So from my half reaction, in this case, 1 mole of aluminum, 1 mole of solid aluminum, goes with 3 moles of electrons. So I'll put 1 mole of solid aluminum and 3 moles of electrons. And then from the periodic table, my grams of aluminum would be, that does not look like a grams of aluminum, hang on. My grams of aluminum would be from the periodic table, 26.98 grams per 1 mole. So now my moles of electrons cancel, my moles of aluminum cancel, and I'm left with grams of aluminum, which is what I was asked. So I'm going to do the math, and when I punch that in my calculator, it comes out as 0.32, and I don't remember, that's what I wrote down. I don't remember if that was exact or not, but we need to talk sig figs. Your current is a part of your sig figs. This is a measured value. You saw how you can measure reduction potential. If we're measuring electrical current, we will measure that. So because that's a measured value, it's the 2 sig figs in this case, so we're going to round to 2 sig figs, and that gives me 32.32 grams of aluminum. So to recap really quickly, we go from time to coulombs, from coulombs to moles of electrons, and then from moles of electrons to moles of whichever substance we're talking about, and we can convert to grams if we need to. Okay, so let's do another example. You may want to pause the video and write the example again. In this case, they ask how long, and so we're solving for time. And they tell me that we want to plate lead. I don't know why we would plate anything with lead, but we're going to plate lead. We're going to plate 15.4 grams of lead. This would be solid lead from a solution of lead 4 nitrate. So I need to remember that this is going to be a reduction from lead 4 plus to solid lead, which means that in this case, that's a transfer of 4 electrons. Okay. And they give me the current, which is required. I can't do this if they haven't given me the current. So remember that the 7.9 amps tells me that 7.9 coulombs equals 1 second. This would be 7.9 coulombs per second. So translate amps, remember, to 7.9 coulombs per second. And that's your second equality. Okay, so we're going to start with what we were given, 15.4 grams of lead. And we're going to just start doing our dimensional analysis stoichiometry here. So I need to go from grams of lead to moles. This is like traditional stoichiometry, convert to moles first. And so this would be 1 mole, and I used 207.2 grams from the periodic table. And I'm trying to get myself to time, so I'm going to have to go from lead to moles of electrons, and moles of electrons to coulombs, and coulombs to seconds. So you want to picture that this is your process. We're going to go from time to moles of substance, in this case lead, to moles of electrons, to coulombs, and then finally from coulombs to seconds. Okay, so this is our process. So we've converted our grams of lead to moles of lead. So now we need to go from moles of lead to moles of electrons. And that's going to come from the coefficients in our equation. So 1 mole of lead, 4 moles of electrons. And from our moles of electrons, we're going to go to coulombs. So this is always by definition, this is Faraday's constant. 1 mole of electrons, 96,500 coulombs. And then from coulombs to seconds, and this is our conversion here. So this would be 1 second, 7.9 coulombs. So I'm going to do the math, and I get 3, and they didn't ask for a specific time, so I can leave it in seconds. If they'd asked for minutes or hours, I'd have to keep going. So my calculator answer was 3,631.5. It kept going. I have from my current 2 significant figures, so I need to round to 3,600 seconds. Okay, and there's my how long it would take to plate out 15.4 grams of lead. I forgot that you won't have this link, so if you're interested in this link, send me an email. It's kind of a cool process about how we plate the pennies. Our copper pennies are really only zinc centers and a little bit very thin, notice 12 micrometers thick, of solid copper. So So if we're gonna, that's very thin, right? So if we're gonna plate our pennies, we use a zinc center and we use a solution of copper 2 sulfate. So what I wanna do is talk about if we wanna plate a penny like that, we wanna know what the current is. Okay, and so that 12 micrometers thick, they tell me is about 0.060 grams of copper. They tell me it's going to take about 5 minutes, and we want to know what's the current. So remember that this means we're solving for amperes, but we can't solve directly for amps, which means we're going to solve for coulombs per second. Okay, so I can already look at this question and see that in the question I was told my 5 minutes, right? So I can convert 5 minutes to seconds pretty easily. You might be able to do that in your head. Minutes to seconds, and so this is 1 minute 60 seconds, which means that this is 300 seconds. And honestly, when it says about 5 minutes, we have 1 sig fig, which is terrible, right? So, but it takes about 5 minutes to plate a penny. So just wanted you to kind of think through that. So this is my time. So if I'm solving for my current, my amperes will equal 300 seconds on the bottom because that's the time. And now I need to use everything else that I'm doing to solve for coulombs, right? So I'm going to start with my 0.060 grams of copper, and I'm going to follow the same process. Grams of copper, 2 moles of copper. This would be 1 mole, and from the periodic table, 63.55 grams. Then moles of copper to moles of electrons. I didn't write a half reaction yet, but they told me it was copper 2. So this would be Cu2 plus 2 electrons, and you might be able to do that without writing the half reaction. So this is going to be 1 mole of copper, 2 moles of electrons, and then from moles of electrons, sorry, that kind of ran together, from moles of electrons to coulombs, and this is Faraday's constant. So 1 mole of electrons, 96,000, I'm sorry, I keep saying that, 500 coulombs. And when I get my answer to this, then I'm going to plug it in here for my coulombs. So I solve for this in my calculator. I get 182.21 bunches of numbers. I have only 1 sig fig coulombs. So I'm going to just use my calculator and plug that in as 182.21, whatever that answer is, coulombs divided by 300 seconds. So the current that it requires to do this is 0.607 amps or coulombs per second, and rounded to 1 sig fig is 0.6 amps. So the current required in about 5 minutes to plate a single penny would be a current of 0.6 amps. So review the video if you need to. Make sure that you have your notes with you, and I will see